And now please allow me to introduce Dr. Alison Graettinger. Dr. Graettinger is a postdoctoral associate at the University of Buffalo Center for Geohazards Studies. Her research includes large-scale experimental volcanology with a focus on magma-water interactions. Alison is a proponent of seizing learning opportunities as they present themselves, as her work requires a combination of scientific expertise and lots of practical knowledge, including carpentry, landscaping, vacuum repair, and crafts. She received her PhD from the Department of Geology and Planetary Science at the University of Pittsburgh. And Dr. Graettinger will be presenting on applications of visible and near-infrared spectroscopy's volcanology.
Actually, that means the microphone. I'm just a generally loud person, so we can skip the mic this time. So, well, I said at the talk, basically we're going to shift gears completely and go from very technical focus on the specific questions of spectroscopy and going to a bigger picture. Okay, we have volcanoes. We want to study them. How can spectroscopy aid in that? And it's a multi-tool bearing kit, and it's applied in different ways using different wavelengths and different questions at different times. So my training is in physical geology. I'm a mapper. I look at deposits. And so I've learned to use spectroscopy to aid that. And I'll give a bit of an overview as well about other applications that aren't from my specific work, but that are volcanology related, that might be of interest. Whoop. Here we go. So I gave my spiel that goes with this. We're gonna travel around the world, but spend some time in Iceland because it is a place of interest to me because the mention of magma and water, that's the questions that I ask. But ultimately, it's the deposits I'm interested in. How can we look at them using different approaches? So when you're interested in a volcanic system, whether you're looking at an active system or one that's erupted in the past, pick your wavelength. You can have a favorite wavelength and look at different elements of the system, or in my preference, I like to combine. So I like the VNIR all the way up through the long wave, through infrared in particular. But occasionally I have colleagues who dabble in the UV or the radar that I can take advantage of their expertise. So you can see in these two examples here, just some of the basic interests of why we're looking at volcanoes. And so there's the ash hazard. If you guys remember the eruption of Eyjafjallajökull in 2010, that ash plume was very problematic for Europe. So it's not a localized hazard, it's a large-scale hazard. So that's why we love satellite imagery. But also then a more recent eruption that happened this past year, also in Iceland, in Planetary, you can see that we're using radar there to map changes in the flow as it grew. And one of the reasons I included this particular image is we're going to return later to this volcano that's actually right next door. That's Askja, one of the few in Iceland that's super easy to pronounce. And we're going to look at deposits along this side here. Volcanoes aren't just on Earth. We can go to many other places, and spectroscopy is our friend because we can't touch it. So this is an example of active volcanism from our solar system. Io is a moon of Jupiter, and there are actively erupting vents. We've seen changes. We've seen lava flows appear. There are lava lakes. It's changing over time, and we can monitor this. One of the instruments that I'll point out just for fun, since this is a VNIR group, the NIMS instrument looks at the 0.7 to 5 micron. You can see my bias towards the TIR there, that I'll be talking about microns a lot more than I'm talking about when we're jumping around with units. But we can also then look at cryovolcanism. So when we look off Earth, our definition of volcanism is anything that comes from inside the planet and out. It doesn't have to be the silicic lava that we think about on Earth. And we actually have a candidate from Pluto, these new images coming back from the New Horizons mission, where we're seeing regions that might be cryovolcanic. So this feature right here, called RIT Mons, may actually be a cryovolcanic feature. It looks very young. Stay tuned, there'll be more data, there'll be more wavelengths as it continues to download from the instrument, and we'll learn more. My workhorse instrument is ASTER. So the satellite has a combination of VNIR bands, Up until 2008, we had SWIR. That broke, unfortunately, but the TIR and the VNIR still work. So if you're looking at past deposits, you can always go back in the archive and take advantage of it. But if you're looking at more active recent events, we can't use the SWIR. And just why some of these wavelengths are interesting in terms of mapping and geology and why volcanologists might care. We can see we have our VNIR versus our SWIR, but some major rock-forming units, of course, showing different spectral features in these different wavelengths. And it's a little subtler in the VNIR, a little bit more dramatic in the TIR, but we can still make major distinctions. And I'll get into some of the applications with some examples from Iceland, like I mentioned. The data in the US is really easy to get a hold of. There's also an Astra-based EDM that's available to everybody. If you want international data from Astra, it's a bit more work. They want you to put in a proposal or work with a collaborator who's part of the instrument team, which is what I do. So for details on that, look on their website, because I have collaborators who make my job easier. I also like things like QuickBird. We can go to much higher spatial resolution, which lets us look at more detailed features. And the important part of QuickBird is that it's not just viz, we also have the IR, the near IR, which lets us start looking at vegetation. And vegetation around volcanoes changes and responds to eruptions and deposit types, and can give us a lot of important information about the rocks just by looking at the plant line. There's also pan-band of these. The lighting in here isn't super. I don't know if we can turn it down for some of my imagery, but one of the reasons I stuck this up here is we can see this dark flow here is actually mud flow, and by adding in the IR band, we can actually see the difference between the mud flow here and logging human activity that actually has reduced the vegetation in a different area. So when you look at the viz imagery, those two little streaks of dark look quite similar, but as soon as we have the IR, we can start to differentiate between this fresh, moist flow versus just some bare earth as a result of human activity. Nope, there's an arrow. Ooh, thank you. Just in time, too, so now you can see what I'm actually talking about. Might be a big dark. I'll try to be exciting to keep you awake, just so you can appreciate the imagery. Here's a similar one. We're still looking at Mayon volcano in the Philippines. Similar deposits, but again, the addition of the near IR, in this case, is from Worldview. We have more bands available. There's 2 IR bands, and the resolution's pretty awesome in these wavelengths. We can get about 2 meter resolution from both these instruments, and with the pan band you go down to less than a meter, which is really good for picking out specific features that we're interested in. There's also lots of other sensors. I haven't covered them all, but these are some of the favorites that get used on volcanoes. So anything from the ALI instrument to Landsat, Iconospot. If you can put it on a UAV, we love it. If you can get an airborne instrument, that's useful too. So volcanologists tend to take advantage of, we're exploiting any opportunities that are available in instrumentation. So not limited to specific spectral or spatial resolution at any time. And temporal resolution is very important for us. So we will take advantage of any data set that we can get a hold of for our target. Now, in terms of the surfaces that we're investigating, they're quite diverse. I have images here of active lava flows, which have their own challenges because an active flow changes, but if you get into different wavelengths in SWIR, you might be saturating and actually not be able to look at it because it's too hot. That's why we need to get to the thermal infrared. In the other cases, vegetation comes back in quite quickly. So this flow over here is only from 1992, and the vegetation has grown over significant components rather quickly. The reason I like to play with different wavelengths and not just be limited to N1 is you can also see here we have an ash plume and then meteoric clouds, and depending on your instrument and what windows you have, they can be quite hard to pick out. So the more wavelengths you have available, the better you can target it. And the final image is just, this is a very practical sort of approach. We need to know where something is going, say ash in the atmosphere, where it is currently, where it has been in the past, things like that. So a lot of it is detection, recognition of different surfaces, and then also detecting change. Change is the big one, especially if you're looking at an ongoing eruption. So here's just another specific application. These are two images from the Aster image in it's just the RGB from the Viz, and then also contrast with the SWIR over here. And vegetation, different flows. We can actually see some of the SO2 gas in the Viz, which is not being picked up in this particular instrument. But if you go out into the TIR at 8.3 microns, you can start to pick up SO2 again. So the contrast of different wavelengths and different images are very useful for detecting different things. We like these wavelengths because the silicate minerals pop up, specific iron oxides, or if we go up to SWIR, we can start to get clays. That's important for hydrothermal alteration. So all of those different elements can come up as spectrally unique. We can map them, we can watch them change over time, things like that. And that's the ultimate goal, is to see what the system did in the past, what the system's doing right now, and then we might be able to say something about what it'll do in the future. So here's just an example of change detection. We're not just talking hot things, we also look at mud flows. That's actually where I started my research. And this is an example from 2007 using the Aster instrument again. And you can just see how well the flow path picked up from the Lahar. It's pointed out there with the yellow notes. That immediately afterwards, a very fresh deposit's pretty easy to pick up. So when you have change, that's if you have a nice baseline understanding of what the system was, lots of imagery, we can better pick out changes like that. We can also look for more subtle variations. So this is some work from one of my colleagues at the University of Pittsburgh, and Ramsey, is looking at Augustine volcano in Alaska, and these were pyroclastic flow deposits. So you can see in this image up here, there's a whole sort of debris fan. Think of it like an alluvial fan, nothing but pyroclastic deposits. So multiple flows, lots of small flows over time, building up material. And then using repeat imagery, you can then look for how much has this changed and trying to quantify that change to say something about the deposit types, the deposit volumes, things of that nature. So this on the left is just an unsupervised classification of Viz imagery from the Aster instruments in those three bands, and just showing the unique spectral groupings on the system. And then if you just pick one of the bands, so this is band 3, and over the 3 years of data availability, looking at how that changed over time. So this might be compaction, this could be a cooling effect, it could be redistribution of material from wind and rain. We have lots of variables in this system. So first step is, where is it changing? And then, as field geologists, my favorite part is we run in and we can go poke at it and see what's changing and why, and then recalibrate the system. So the next time it happens, we might have a better arsenal of approach for solutions for what might be changing. Here's just an idea of some of the diversity of the land surfaces that we're interested in. In some cases, you can see that we just have color variation. We have steep slopes a lot of the time. Here's hot rock next to cold rock. You can have all of this material is predominantly the same composition, but you can see grain size and texture is very different within that image. We can have compositional variations over different scales. This is actually the crystal size scale. We're now in the millimeters. Or centimeter size change, so 10 centimeter size change in this image. We do have vegetation. Volcanoes don't kill everything. Sometimes it returns quite rapidly, and you also have water. It's a steep slope system, so it's very dynamic. There's lots of elements contributing to our spectra. And this is an image where everything is actually really similar in composition, but still texturally different. So here's a case study. We're now at a volcano in the US. This was an eruption in Colorado. It's the youngest volcano in Colorado. And you can see there's a crater feature here. This is a specific type of volcano called a mar that's the result of an eruption from rising magma meeting water, and you have a very explosive eruption in the ground. So what you're doing is excavating a hole in the pre-existing rock. So inside the crater, this red is just the original material. It's a sandstone. It's not volcanic. Where did the deposits go? So that's the big question, is where's the ash and the tephra that was produced by this eruption? First glance, our grad student comes back and says, I think all of this lovely material over here might be ash. It's 5,000 years old, it's an arid environment. We shouldn't have a lot of soils. That kind of made sense. We went in the field, and here's our crater again. We dug some pits of the proximal deposits, so we're on the crater rim. We know it's related to the volcano. And then we start looking for the ash elsewhere. And we found this instead. It's actually a burn scar, which is also common in the desert. So the answer was, or the question came, well, where did this ash go? And we sent a graduate student out. He had so much time. Go dig some holes. Because back, I dug a lot of holes. I can't find the ash. So remote sensing and spectroscopy is now the next step. Okay, the ash has to be there somewhere. And what has happened as a result is I'm actually suspicious of this age. If it's only 5,000 years old, is there a significant soil on top? Is that why we can't find it? Or was it blown away? And we need to keep looking for it to find that out. So just first run, pulling out the Aster Viz, looking for spectral diversity in this scene. Here's the crater for reference. It doesn't actually have a spectrum coming off it. We only have 3 bands in the Aster here, but it's pretty easy to see there's some diversity with that host, that red sandstone that I pointed out. There's some vegetation, the scrub that's sort of come back in and grown. And then this area where we thought the ash was, we actually have 2 different looking spectra. They're not hugely different, but what this does is gives me someplace to send that poor graduate student. So he's not trying to cover this whole scene. He's trying to get to targeted areas and look for ash that hopefully is there. If not, we'll keep investigating and look for a different mechanism. So a more complete study that actually has a bit more of an answer than that last one takes us to Iceland. So this is that volcano Askja that I mentioned, the Hulahrön eruption that I mentioned before. That was just this last year. Would sort of be poking into this imagery if I had a newer image. So it's kind of fun to watch that because my volcano was always in the background on TV. They weren't talking about it. Anyway, so the surface at this volcano has a lot of diversity. I should have showed you some examples earlier. This is a pumice in the foreground, so it's high silica content over the basalt, which is a lower silica content, more iron and magnesium. We also have snow. This is the center of Iceland, so even in August, where these images were collected, the snow does not go away. Some years the snow didn't go away at all, and you would actually not be seeing the rocks, period. So it makes it kind of difficult for the duration of the study. At the time, there was only 1 image in all of the Aster archive from 99 onward that had a clear shot of this volcano. Recently, there's been a second image. I'm kind of excited. I'll go back and look at it again. But there's also here some lava flow in the foreground. This is made of the same material. This is basalt, but it's fragmental. So very different textural signature. And the goal was to go in, look at the rocks, find the diversity of lithology. What are our different rock types? What's making up this feature? And then can I say something about the nearby volcanoes calibrated off of this one detailed field study? Because I don't have time or money to do a detailed study on every volcano. And maybe 1 or 2 might be really ideal to go back and look at. So here's Askja at the bottom. All of these other lumps and high topographic features are mapped as the same stuff. They all say magma and water interacted. There was a glacier here. We had very interesting eruptions. That's all we're going to say. I'm very interested in those details that they brushed over. So the goal is to take one volcano and extrapolate it out and see what we can say about the others. So once I found this lithological diversity, take end members, bring back these end members, create a spectral library, and then use those end members to do classifications and see if we can't produce a map from there. So here's just an idea of some of the diversity and the awesome landscape that is Iceland. I'm always an advertisement for tourism to Iceland. It's a gorgeous place. And you can see this is the map that's produced. So this sort of arcuate shape here is the area I mapped. Previous maps lumped this as purple. So all of these massifs that I'm talking about are lumped in now as subglacial, and I want to pull out some of this diversity. These are some examples of the end members that I brought back to the lab. This is basaltic, this is basaltic, this is basaltic, this is basaltic. But you can see that while the composition is fairly similar and overlaps, there's a lot of textural differences, and at least in some cases you also have alteration features. So this is starting to break down into a clay called palagonite, sort of a family of clays with a funky material. It's all over Mars, so we're also interested in terms of other planets. This is a rhyolite, and this is a rhyolite, but again, very different texturally, and also one's altered. So those were my basic end members. And here's just an example from the Viz collecting the hyperspectral. It was a field spec. Did this in the lab, very short path length, no worry about changes in atmosphere, nice calibration. And you can see that the rhyolites sort of lumped together. There's this, the lava versus the pumice, and then the basalts lumped together. But we have some slight variability as a result of that texture here in the Viz. It's more dominant in the TIR, which I did the exact same thing, and then we resample it for the ASTRA instrument. So we have calibrated hyperspectral data from the field, and then we take this back to our few bands of satellite imagery and look for our targets. So first pass, sort of, let's do some unsupervised classifications as well. And you can see this is just the RGB, but then we have some features that start to stand out. This is your lake. The lake feature stands out again for in all of the images. And you can see sort of systematic, there's important features that keep standing out, no matter how we try and classify the image. So they are spectrally unique, and then possibly lithologically unique. There's this sort of swathing feature that I'll draw your attention to. And then there's blue everywhere in this image. There's a lot of similar features in the field. And really, geologically, there's some consistent themes. There's volcanic rocks of two types, so basaltic and rhyolitic, as you've seen from the previous images. And then there's all this redistributed sand from aeolian processes or glaciers or things like that. And then odd bits of vegetation poking out in water. But when we get to the supervised classification, where we're using these end members, we can actually pick out specific, this region here where I mapped is highly spectrally diverse, just like I was seeing in the field. And so these more consistent areas then stand out for being more consistent. But here's another highly complex unit. Here's a more complex unit. This over here is spectrally complex as well. And those previously just mapped as purple subglacial volcanics. So that was kind of an exciting outcome. So now they're pink. I'm sorry, I was calling them purple the whole time, but I've swapped it in the map for you. But all these other blobs that were just mapped, oh, it's a subglacial volcano. And this is the area I mapped. Then when we combine these multiple wavelengths and using supervised and unsupervised classifications, looking for consistency in these groupings and a little bit of manual interpretation, we end up with a final map where there are two major groups in these purples that get broken down, and that's the fragmental versus the non-fragmental units, which is actually very important from a volcanological standpoint in terms of how that erupted. So is it explosive or not explosive? That's always a good question. Another important thing that we drew out of this, you can see this yellow, and the viz was actually really key in pulling this out, was that pumice that covered up a lot of the areas I was interested in. So I wanted to understand the eruptions that were made of basalt, but in 1875 there was this large eruption that blanketed everything in pumice. Now it made things accessible. I could climb much steeper hills as a result because pumice makes for nice climbing, but it did also make it more difficult to do remote sensing over this feature here. So being able to determine where that pumice was remotely, currently, not just where it had been initially after the eruption, which is a nice isopack of continuous deposits. So we can start to pick out some of this complexity of nearby features. We can pick out complexity on a feature that I already knew was complex. Ground-based opportunities in volcanology are sort of endless, and this is a realm that we're starting to break into using a range of hyperspectral instrumentation. But basically the goal is you go up to a vertical face and you say, aha, it is made of many diverse things. I don't have enough time to rappel down that and collect every single unit, though I'd love to, it's fun. If we get a few calibrated end members, the same way I did for the satellite-based work, then if I can collect one or two spots, then we can come up with a map of what's going on this using various imagery and different wavelengths. And the same for this, and we can then unravel how that particular series of deposits was in place, which gets us back to processes, which gets us back to hazards, which is ultimately one of the big goals of volcanology. We want to know how, why, how much, etc. And then the reason that my introduction include discussion of carpentry and vacuums and things like that is we do large-scale experiments at the University of Buffalo. This is a Geohazards Center that's basically been doing volcanoes right now. So anybody else who's hazard interested, we have this large facility. It doesn't just have to be volcanoes. It's a user facility where people can come in and make a mess. The mess that we've made has involved dynamite, and at the moment we're melting our own lava. So that gives you an idea of how much of a mess we can make. Earth moving is not a problem. Make your own dunes over a certain size, whatever, totally possible, and then you can have a certain level of calibration at a larger scale than you can get in the laboratory. But where spectroscopy is starting to play a role there, as you can see, it's mostly in the IR based on these sort of overly colorful imagery. But introducing additional wavelengths is just one of the ways that we can quantify these processes. And they're at a larger scale, they're slightly messier. If you ever want to test an instrument, we've actually done a lot of that. So some of our colleagues have done a lot of work of refining their high-speed thermal infrared cameras using our processes. We had other people doing geophysical testing, stuff like that. And then just for fun, because there's an explosion in the middle, I'll point out what we're looking at. So these two are an explosion. This is in the IR. This is what it is. Then there's this lava flow furnace. At the moment, I'm just basically going, where are we losing heat? I'm not even looking at specifics of the spectrum yet. And so that's the furnace, just with a regular picture, and my colleague wearing a silver suit. We made ourselves a little lava cake. You know when you go to a restaurant and they give you a molten lava cake and you cut it open and goo comes out? I did that with real lava. That was like last week. I'm pretty excited about that. Anyway, we can look at these different little lava flows that ooze out the side and the temperature, and so I have temperature profiles to go with it. And I'm very interested in the mixing of the sediment and the lava, and temperature is an important part of that. And so I can use different wavelengths to look at it texturally. I can also use those to measure these temperature profiles. So there's a lot of different ways to play with the electromagnetic spectrum and volcanoes. So sort of summary for if you were to learn anything about what volcanologists care about in terms of using remote sensing and spectroscopy, it's just locating future areas to go study. We can't study them all. How do we narrow that down? Change detection that we can do remotely, and you can study a lot more places that way. We're ultimately interested in deposit sizes, but also deposit characterization. So I'm quite interested in discussions about grain size and different mechanisms of being able to identify that using spectroscopy. And then vegetation health, I mentioned before, is one of our key tools. So if you put this in sort of the hazards perspective, you can take it into ash crops and livestock. So how does that crop respond to being covered in ash or being affected by SO2 gas and other toxic gases from volcanoes? Where's that ash? How's it going to kind of plain avoid it? And the VIS through TIR range is really key to this ash problem. Gas seeps, so sometimes gas comes out of the ground not at the vent, and the easiest way to find that is remotely. You can look for vegetation health, so the near IR is very important for that. And then thermal anomalies, or watching where snow is, was, and where it might be if you put hot stuff on it and it melts and wants to run downhill. So it's sort of a lot of people's careers mashed into a short thing, and a few of the bits of how I use it myself. But if you're always interested in branching out and taking your spectroscopy knowledge, there's volcanologists who probably love to work with you. And I'll take any questions.
All right, everybody. So that concludes our morning session. We have lunch prepared for you in the fishbowl that's out to the left as you exit the auditorium. And then we will be back in this room at 1 p.m. for Dr. Philpott. Thank you.